Hello, my name is Shufil Azum. I'm the Senior Consultant and Subject Matter Expert in the areas of Safety Management System. Today I would like to go over the analytic framework for systematic screening of roadway departure crash. My study area is the rural highways in Montana. I would like to also acknowledge the co-author of this study, Ms. Patricia Burke from Montana Department of Transportation. So let's take a quick look at highlights of today's presentation. I would like to have cover three different areas in my presentation: the roadway departure crash itself, the challenges and the strategic objectives. Then I would like to go over the analytic framework. There are three different areas I would like to discuss today: the crash data driven analysis, network screening and hotspot identification. Finally, the proactive screening. In my last segment of this presentation, I would like to cover the couple of case studies. The first one is the analysis of crashes with drivers distraction. As we know that there are a lot of crashes that are happening due to drivers being distracted and getting departed from the roadway. So we'd like to cover that aspect. And there is another study, the network level funding decision, and how the framework can help you making decision in taking the initiatives for road departure crashes. Let's start the first segment of the presentation. Roadway departure crashes caused more injury and fatalities than any other crash type. This is due to the fact that drivers lose their control of the vehicle and can go into the ditch or water body, or can hit an opposing traffic or fixed object. These can have severe consequences. In the United States, there are roughly 54% of fatalities from roadway departure crash. If you compare this with Montana, it has roughly 64% of the fatalities due to roadway departure crash. Roadway departure crashes categories can be broadly classified into three distinct categories: the single vehicle rollover or fixed object crash, the multi-vehicle head-on crash, and the cross-median crashes. Now let's compare the crash trend in Montana. If you look at the total fatalities, there are roughly 200 fatalities per year, and this is pretty much steady. There is not much reduction. If you compare the crash trend of the roadway departure crash, roughly 140 crashes per year, so this is roughly 64% of the average. There is an increasing trend up until 2012, and there is a decreasing trend from 2012 all the way to 2014. Now let's talk about the strategic objectives of roadway departure crash types. There are three different aspects we'd like to talk here. The Federal Highway Roadway Departure Strategic Plan. This is the initiative taken by the federal government, and they have laid out their plan for the roadway departure programs that DOTs can follow. So Montana is all developing their CHSP and definitely considering some of that aspect from Federal Highway in developing the CHSP plan. And finally, Montana also developed the analytic framework that can contribute to the CHSP and also can help them identify the issues on the roadway and can make a better decisions on their countermeasure selection. So this is how the framework looks like. If you can want to compare that framework with different roadway departure initiatives taken by Montana, there are three different areas we can discuss. The first one is the analytic framework that Montana Department of Transportation has, and we already discussed there are two different initiatives taken by Montana. The first one is the roadway departure study. It has the roadway departure related safety performance function, and then there is a data-driven analysis using the safety information management system. And in this information management system, which is basically the AgileAssets safety analyst, Montana is using that in very different aspects. First of all, is helping them running the network screening and identifying the select countermeasures, and they are composing projects and doing benefit and cost analysis within that framework. Also, this is helping them developing their CHSP in various aspects of CHSP when they need any information, like how the crash chain looks like, what are the different emphasis area they need to focus on. These kind of questions are all answered by this analytic framework in the safety management system. Secondly, we have the engineering solution, and there are both short-term and long-term solution for that. So if you want to compare the short-term solution, we have the shoulder and center line rumble strip, delineation, and signing. And there is some long-term engineering solution that cost more money. So, but eventually, state can consider that. There are shoulder widening, slope flattening, and curve reconstruction. Those are all under long-term categories. And the third one is the enforcement, media campaigning, and education. So Montana also has this kind of program. Now let's summarize the strategic objectives of Montana Highway Safety Plan. Montana wants to reduce and mitigate the roadway departure issues through data-driven problem identification and best practices. They're putting the emphasis on the speed-related roadway departure and intersection crashes, and they're also considering the education and media campaigning as one of the emphasis areas to reduce the roadway departure crash. The two more objectives to explore and implement the best practices to reduce the behavioral factors like the distracted driving and the fatigue driving, and then the improvement of the prosecution and adjudication of all roadway user violations. Next section of my presentation, I would like to go over the analytic framework, which is the main topic of this presentation. Now let's go over the analytic framework. There is the first one is the crash data driven analysis. In this case, anyone who is running the analysis doesn't need to run any systematic network screening to answer their question, to identify the areas. Basically, we can just deal with the roadway departure related crash data, basically apply some filter on the overall crash record so we can narrow down the search. And then with the aid of different visualization tools, we can come up with the solution and then do the project composition and benefit and cost analysis. So this is the first aspect of that. Secondly, there is a more systematic approach. We can use the network screening and hotspot identification technique in the safety management software, and here we can do the diagnosis and follow the highway safety manual recommended process, and eventually can come up with the project composition and benefit cost analysis. Then there is a third aspect. In this case, we do not necessarily need to start from the network with or do not need to start from the crash. We can actually look into the geometric deficiencies on the roadways and can come up with a plan to mitigate those, so can have some engineering long-term or short-term solution for that. This is what we call the proactive screening. Now let's take a look into the overall data-driven analysis framework. So we're starting this framework using the safety information management system. The first thing is that we can do some query on or reporting on the crash data. And if you want to see an example of that, this query can be very simple or it can be very complex. This is an example of a complex query. Here we are pretty much doing a data mining of the crash data. We have the rollover and fixed object type of the crash. We can then have a filter on the rollover crash with respect to the grade or curvature of the roadway, or whether there is a guardrail or tree presence or not. And based on that, we can come up with, okay, if it's a grade, that can be level terrain, can be rolling or mountainous. So this is how we can identify the engineering aspect of that, or if there is any engineering or geometric, there is any geometric issues related to the roadway departure crashes. And finally, we can also investigate the behavioral factors, like for example, we have in our crash data the different distraction. So if the driver was distracted, whether it was related to cell phone or some other things, or there's no distraction, that kind of information is there. So we can definitely use those information to identify the behavioral factors. So the next step is identifying the roadway and behavioral factor. This is how we can do that. And finally, in order to make a better decision, we can plot these subset of the crash in the GIS map. So it's called GIS based diagnosis. And once that is done, we can identify the project and do economic justification for that. An example of the GIS based diagnosis. What you can see in this example, that we have a subset of crash and we are using the visual aid, the GIS, to identify the issues. And in this example, we can identify the spot where there are a lot of roadway departure crash, and there is also some geometric deficiency that we need to deal with. So what you can do, we can definitely take that specific area and use other visual aids, like for example the satellite image, and take a look into that. Or we can use the video log or maybe the Google Street Map to go over one step down and take a look into the issues. What in this specific example, I can see there is a curvature, and I can go along the roadway using the video log and try to find out whether there is any warning signs or not, to find out the existing engineering solution in dealing with that curvature. Now let's take a look into the network screening and hotspot identification part. Network screening is a structured framework, and it actually starts using the safety information management system. We establish the crash filter for the network screening, and then we also have the safety performance function we already discussed, that Montana has the roadway departure specific safety performance function. Then we run different network screening scenarios and then identify the hotspot by level of service of safety method. And finally, we maintain and then this selection of countermeasures, followed by benefit and cost analysis, is a functional form of the safety performance function. So you're using this function first to identify the predicted crash count, and once we have the predicted crash count, we're adjusting that with some weighting factor, and also using the observed crashes on the roadway to find out the empirical base corrected estimate. Here is a better illustration of this process. So what we can see here, that the blue line, which stands for the safety performance function estimated crash count, and we have here the upper and lower boundary. Upper is 80th percentile and lower is the 20th percentile. And then we can also see that dots, the blue dots, those are all empirical base adjusted crash count. So what will happen, that this specific the mean value and the upper and lower will eventually distribute the domain into 4 different zones, level of service 1 through 4. So based on where the empirical base adjusted crash count located, we can identify the level of service of safety. And we can also define the rule that in what condition we will consider that specific location as a hotspot. The important aspect of network screening is the creation of network profiles. Network profile can pinpoint the location where safety problem exists. And goal of the profiling is to partition the network into smaller pieces. It also implements the HSM recommended practices. Like for example, we have 3 different segmentation criteria defined in Highway Safety Manual: the peak searching, sliding window, and simple ranking technique. For the peak searching and sliding window, the network needs to be divided into subsections, and the network profile can be used for that. As you can see in this slide, there is a roadway network which is longer. It can be the whole route. We are dividing that into the major segment of 20 miles long, and each of the major segment can also be subdivided into smaller pieces. If it is a peak searching technique, then those subsections will not be overlapping. If it is a sliding window, then this subsection will be overlapping. Sliding window gives us a benefit that it has a more dense distribution, so it really helps to pinpoint the location of the safety issues. Here is a snapshot of the network screening window in AgileAssets safety analysis system. As you can see that this window has 4 different panes. The top left pane is called the scenario pane. Here the user can create a scenario for the network screening and can define the associated crash filter or network filter, and also the year of ADT for the analysis. On the bottom left pane, there is a crash percent threshold pane. So when your user is running any scenario, it basically captures the threshold for that specific scenario. On the right hand side, there are a couple of pane. The top one is for the main profile location. It captures the main profile location results, and the bottom of that pane there is a secondary location profile. As we discussed in our previous slide, that network profiles basically creates the main profile location and the secondary profile location. So basically those sections are all stored here along with the performance measures. And there is also a tab, as you can see on the top right corner, we call it the hotspot tab. So when the network screening is done, the identified hotspots are saved in that specific tab, and user can do further analysis using that tab. Now let's talk about the proactive screening framework. In the proactive screening framework, safety users can run a screening on the roadway to identify some of the geometric deficiencies and can have a long-term safety plan for that. In this framework, the first thing we need to maintain the roadway inventory, and that roadway inventory can be based off the Meyer element, which is model inventory roadway element. And after this roadway is defined, then we can also define a decision matrix for that. So decision matrix is basically, it will identify a correlation between different types of geometric deficiencies and can rank the deficiency from high, medium, and low. And then based on each of these deficiency, we can also establish the recommended treatment for that. Once this decision matrix is set up, we can run the we can also set up the network analysis for that, and then can establish the framework for optimization. And in this framework, we can define the objective function and different constraints for that. And finally, the end results of that optimization will be the work plan that we can consider for the long-term safety investment. Here's the conceptual framework of the proactive decision matrix. In this example, you can see that we picked up the roadway width as an example for roadway feature. In order to establish a decision matrix, we need to compare the existing roadway width with the required or standard width. So what you can see that we have the required width of WR and we have the standard width, or which is the standard width, and we also have the existing width WE. We're comparing that. Then based on the extent of deviation from the standard, which is delta 1, delta 2 or delta 3, we can define the defects as high, medium or low. Finally, we need to link a specific treatment option to the defect category. In general, defects with low severity has lowest cost for treatment, and the severity increases as the cost of the improvement increases. In the next segment of my presentation, I would like to go over two different case studies. The first study shows an example of crash data-driven analysis, how an analytical framework can help identify the distracted driving pattern in the roadway departure crashes. The second study, it will show you an example of network screening, how the network screening results, we can use that to distribute funding among financial districts. The objective of analyzing the crashes that involves drivers distracted by cell phone is to identify the behavioral pattern of roadway departure crashes. The method that we are going to use is simply running query on the crash data itself. In order to identify the behavior, we need to generate some panel data by jurisdiction and crash year. Finally, we can use this data visualization technique to identify different patterns. Some of the key visualizations are, for example, checking the split of this type of crashes in rural and urban areas. Since rural crashes, it can be sparsely distributed. It may not be easy to look into the distribution of rural areas only, but the urban areas like cities can be ranked based on the crash counts. So one of the interests could be the distribution by urban areas only. Finally, in order to identify the crash trend and whether the crash rural and urban areas have any significant difference in the crash distribution, a comparison of rural and urban crash trend can also be analyzed. Here is the distribution of roadway departure crashes while drivers using cell phone over the major cities in Montana. It shows that for the analysis period from 2010 to 2014, Billings, which is one of the cities in major cities in Montana, has the highest number of crashes, followed by Great Falls and Bozeman. However, if we only consider the percentage of total crashes, there are roughly 5.3% of such crashes is happening in the city of Billings. If we sum the major cities, it is about 20%. Therefore, it might be interesting to compare the distribution of rural versus urban areas, since apparently there are more percentage of such distracted driving crashes in rural areas. Therefore, we got the motivation to compare the rural versus urban crash trend, and it shows that there are more run-of-the-road crashes due to drivers' distraction in the rural areas. However, in recent years, there is an increasing trend in the urban areas. And this sort of study can not only identify interesting crash distribution pattern, but it can also help roadway agencies like Montana Department of Transportation develop better education and media campaigning program in specific areas of interest. Now let's take a look into the second case study. The objective of this study is to identify the funding for roadway departure initiatives based on the network screening techniques, and these initiatives can be in engineering, education, or enforcement. The method that we are using is running the network screening technique, which is more structured and robust. And we are also using the safety performance function as the performance measure indicator. And as a horsepower selection criteria, we're using the level of service 4. Here Here also we can use data visualization technique to display our results, and some of the distribution could be distribution of total number of crash by financial district or any other jurisdiction, distribution of the summation of hotspot length by the jurisdiction, and displaying the treatment along the roadway. Now let's talk about the results. It shows that the total number of roadway departure crashes by financial district along with the summation of total hotspot length. As you can see that Mozilla has the highest number of crashes, about 1800, and it has also 160 miles of roadways identified as hotspot, which is level of service 4. If you then compare, the second highest is actually Billings and followed by Butte. Although if you compare the total number of crashes, Butte has slightly higher number of crashes. Here's an example of the roadway attributes in safety analysis software, how that information is stored. What you can see here that there are 3 different Meyer element tables. We have the segment features, the intersection and approach data, and the ramp element. And here is a snapshot of the roadway, the segment, and you can see that there are different Meyer elements that can be part of this table. And this table can be used, this information can be used in identifying the roadway deficiencies along the roadway, which is the proactive map approach, the third analytic framework that we discussed in this presentation. Now finally, let's take a look into the proactive scoring along the roadway. So what we discussed in our previous slide, there was an example of the Meyer element for the roadway, and we can actually track individual element along the roadway. And as we discussed about the decision metric, we can identify whether that specific deficiency is medium, high, or low categories. And it shows in the color coding different severity. The red being the highest severity, followed by the yellow, which is the medium severity, and the green is the lowest severity. And what you can see, for example, if you compare the unsuitable barrier at roadways, so we're trying to figure out whether the barrier is suitable or not. If it shows that the roadway between 65.5 up until 67.5, so this 2-mile stretch of the roadway, your barrier is not suitable. So if it is a sharp curvature and the barriers are, or the guardrails are really important at that part of the roadway, then we need to make sure that this is immediately taken care of, or we fix the issue. And there is then with 68 miles, 0.5 miles of roadway, the barrier looks good. But beyond that point, there is one more areas from 68 to 65.5 miles. There is another high severity zone in terms of the adequacy or usefulness of the barrier. So in this sort of proactive scoring along the roadway can really help the safety decision makers to identify the issues, and that is the starting point of running the hotspot and the optimization, definitely, to make sure that we have enough, we have a plan for future. That was pretty much the main presentation section. Now I'd like to cover some of the conclusions. The analytic framework that we showed you, it consists of 3 different frameworks. The number 1 is the crash data driven analysis, number 2 the network screening, and number 3 the proactive screening. The crash data driven analysis is very simple, but it requires the expert judgment. This This method can also help identify the behavioral patterns like distracted driving. We showed you the example. Network screening, it was very structured and industry standard for hotspot identification and project selection process. Performance function calibrated to local condition is important for network screening. Then you also discuss about the proactive screening, that the proactive screening can generate the safety work plans for long-term safety investment. And we discuss about the overall framework that consists of defining the decision metrics, running the optimizations, and generating the work plan. The framework that Monton establishes, it helps establish the goals, objective, and emphasis areas for the highway safety plan. And also the framework can help utilize the limited resource to achieve the highest level of improvement. With that, I would like to conclude my presentation. If you have any questions, feel free to contact me. Here's my contact. And thank you everyone.